In this video, we're going to be talking about Taylor's theorem, which gives us the error between the actual function and what our polynomial approximates our function to be. So that's what we're going to be talking about, is the error. How off are we? Okay, to measure the accuracy of a polynomial, okay, you have your exact value. You have the exact value, the exact function, say cosine of x, is equal to our polynomial approximation plus the remainder. So our error, or what our remainder is the function minus our polynomial. And there's a formula for this. Okay, and a lot of books have been calling this Taylor's theorem. Okay. And it is often called the Lagrange form of the remainder, or Lagrange error bound. Okay. So when you're looking for, when you see these words, this is what you're going to do. Okay. So we have our polynomial, like I talked about. Okay. So our actual function is approximated by some polynomial plus our remainder. And our remainder. Okay. And this is, it seems like a very scary formula. It's actually not. Okay. When I first revisited this, when I was first teaching the class, I was like, oh my God, that's overwhelming. But no. Okay. So remember, n is the term. So you're basically going to the next term. Okay. So say I use a fourth degree polynomial to approximate, we're going to go to the fifth degree. Okay. And then this is the highest value of the derivative. Okay, on the interval where we're approximating. Okay, between some x coordinate and some c, the center. Okay, so on the interval from x to c, what's the highest value of that derivative? Okay, and then this is the value that so eventually we're going to plug in where we're approximating this at, what the center is to the n plus 1. So really think about it as almost like you're looking at the next term. Okay, and what you have to remember is this function here, this derivative, this is the highest value of the derivative on the interval. And I'll go through an example with you guys. And we'll go through it right here. So our fourth degree Maclaurin polynomial, okay, for cosine is given by that function. Again, this is something you want to memorize. Technically, in this section, our book hasn't taught that to you yet. I know I have, but keep that in mind, okay, is that this is something that you want to have memorized. So our Taylor's theorem, we want to use Taylor's theorem to approximate cosine of 0.1 by using that polynomial and determine the accuracy of our approximation. Okay, so we know that the cosine of x is approximated by this polynomial. Plus our remainder. Okay, so what this is this is approximately 1 minus 1.2 factorial x to the fourth. I'm sorry, I'm already thinking about something that I want to say to you. X squared plus 1 over 4 factorial x to the fourth plus the fifth derivative, so the highest value that the derivative takes on, over 5 factorial x to the fifth. Okay, sorry, I was looking at my notes. So the cosine approximation of 0.1, when I plugged in 0.1 here, I get this approximation to be this. Okay. So we know that our remainder is going to be somewhere between 0 and remember that remainder is given by the fifth derivative. The fifth derivative of cosine is technically negative sine, but we look at the absolute value of that. So sine at our value z all over 5 factorial 0.1 to the fifth. And that's going to be less than, okay? So how I get this value here is I look at that formula. I look at that formula for inverse sine, sine of 5 factorial times by 0.1 to the fifth. What is so this is that fifth derivative. So this is the fifth derivative. Technically it's negative. I don't know why our book doesn't put absolute value signs in there. We should have absolute value signs in there. The highest value that sine takes on, no matter what, is 1. So this is going to be 0.1 to the fifth power over 5 factorial. So when I'm looking at this like this. Okay, so our remainder is somewhere in between. When I calculate this in my calculator, I get 1, 2, 3, 4, 5, 6, 7, 8, 3, 3, 3. Notice how I didn't round, okay? So I know that the cosine value of 0.1 plus my remainder at my fifth term is somewhere between the adding and subtracting. So I add this number to that number and I subtract it. So when I add it, I get 0.99500,425. When I subtract it, I get 0.99500416667. So I know that the cosine is going to fall somewhere in between here. Actually, you know what? Oh, 2, 5. Actually, I didn't subtract it because we were looking at 0. Okay, because basically the remainder gets added to the last term. Okay, so we know that the cosine of this is somewhere in between there. You're welcome to find cosine of 1 in your calculator. I think it works out to be 0.995041, I think. I can't remember. I did it last night and now I can't remember what it was. Okay, next one, next example. So here, find the degree polynomial for p sub n, expanded about 3 that be used to approximate ln of 3.1 so that the error is less than 0.01. Okay, so in this case, they don't give us the polynomial. We have to come up with the polynomial or the nth term. Okay, so if you remember going back here, let's see if I can guess the correct screen. Oh, it's this screen. I gave us these formulas. I gave us the formula for ln of x versus, I gave us ln of x plus 1 versus we needed the ln of x. So we can adjust this to get us what we need for ln of x. But what I actually want to do is I lied to you guys. I want to do something different. I re-looked at my notes and I want us to look at, okay, our function. Let's see if we can come up with a pattern. Our function is ln of x. Our first derivative is 1 over x. Our second derivative is negative x to the negative 2. Our third derivative is 2x to the negative third. Our fourth derivative is negative 6x to the negative fourth. So hopefully you're seeing something of a pattern here. Oh, I don't want that n factorial. I wanted to write in x to the n. So hopefully what you're seeing here is, notice how the power was the same. The power was the same as the derivative. Power was the same as the derivative. You have n minus 1 factorial on the top, okay? And then they reciprocate, so you have n equals 1. So when I'm looking at my n plus 1th term, I don't like how I wrote that, value of the derivative, okay, we're looking at negative 1. I just plug in n plus 1 anywhere I see an n. So I get negative 1 to the n over n with an n factorial all over an x to the n plus 1. So we're looking for the remainder centered about 3, approximating ln of 3.1. Okay, so my remainder, and I don't know what term this is going to be. I take the absolute value of the n plus 1 derivative evaluated at that z point, so at 3.1, all over n plus 1 and remember, this is the formula, okay? So this is the formula for, this was just the formula for the derivative, I apologize. This is the whole formula for the error, okay? So the remainder at 3.1 is equal to, okay, so the value of the derivative, so that is, and its absolute value, so I could take away this negative 1, n factorial all over z, because that's what our x value is, n plus 1 times by 1 over n plus 1 factorial times by 0.1 to the n plus 1. Ooh, so I have a lot going on here. Okay. Simplifying this out a little bit. The n factorials cancel, so I end up with 0.1 to the n plus 1 all over z, that's not a 2, it's a z, to the n plus 1 over n plus 1 factorial. Okay, so on this interval, z is somewhere between 3 and 3.1, between the center and where I'm approximating. Okay, and I need this error. Okay, I need this error, this 0.1 to the n plus 1 over n plus 1, because I'm looking for the term number to be less than 0.1. So I'm sorry, 0.001 from here. So what I did in my calculator is I just went through and I guessed and checked, and I started plugging in 1 for n, and then I plugged in 2 for n. And I'm noticing, looking at my thing here, I shouldn't have those exclamation points there. So again, I plugged in 1, I plugged in 2, and it worked out at 2, this value was less than that. So let me do a quick recap. Okay, so first I had to find a pattern for the derivative. So that's what I did over here, is I found a pattern for the derivative. So I could get a formula for the n plus 1 derivative. Next, what I did was I plugged in this, I looked at our remainder. So this is the remainder formula, okay, where the x is where I'm trying to approximate and 3 is the center. I went through and I plugged in the function's derivative, this piece right here, and then I went through and I simplified. Now, if z is somewhere in between 3 and 3.1, this value's going to be less than this value. So I kind of took away the z. And then from here, I just, in my calculator, went and found the values. Okay, so you might be asking yourself, why am I doing all this? And I think that this is a really good example of why we're doing this. So use the power series approximation to approximate this integral with an error of less than 0.001. Now, I don't know how to find this without my calculator, but that's why we're learning these series. So we know the sine of x, polynomial approximation, is x minus x to the third over 3 factorial, and I don't like something I wrote there. I'm going to say this is an approximation. And I'm going to give myself a bunch of different values, and it goes on forever. So I know that the sine of x squared, so I'm just changing all the x's to being x squareds, turns to this. I'm hoping I don't need more terms than that. Okay, but now what I do is I integrate both sides. So the integral of sine of x squared dx is approximately, now I integrate this side. So I integrate that side and I get okay. And continuing on, and then I would have to evaluate this from 0 to 1. If I plug in 0, I get zeros. So if I plug in 1, I get 1/3 minus 1 over 7 times 3 factorial plus 1 over 11 times 5 factorial minus 1 over 15 times by 7 factorial. And I could keep going. We're going to see where we need to go. Okay, so what you want to look for is you want to look for the term number that is less than this value. Okay, so we know this one isn't. Do I have a calculator here? I have all this craziness out. When I plug in 1 divided by 7 to the 3 factorial, oh, I have it here from last night. This value is 0.023, but we want our error to be less than this number. This number is not less than it. Remember, the error is found in the next term. So I plug in that one, and I get 0.000775. Okay, that's still not less than that value. So finally I plug in this value, and so I get 0.0000132275. So this is less than it. So this is my error. Remember, the error is found in the next term. So if I sum up all of these values, so I can say that this is approximately equal to the sum of those three terms. When I sum up those three terms, I get 0.3102813853. Okay, so that's a good application of where you might see this and what we're actually doing here. We're going to be doing a bunch more examples. Hopefully, through doing some examples, we will get a lot of your questions answered. I know that this is typically a hard lesson. It's one that I kind of struggle with, I'm not going to lie. But I hope that you enjoyed the video. Hope the video was helpful.